Well, thank you for coming. As you can probably notice, I'm still kind of battling a cold, so my voice is not great. Hopefully it will not give out. And also, I will probably try to rush through this. So if I skip any details or like something's not clear, just like ask me. But I will try to get through this like soon as possible. So first thing we need to address is the cringe in the title. Where does it come from? Last month, after the meetup, we were talking about like, yeah, we need someone for the next month. And I was like, yeah, I have no ideas. And after that, we were also talking a lot about LLMs and stuff like that. And then Google decided that we all want to use Gemini because it's a great thing and like enrolled all of us. So I decided, yeah, let's see. So I went like to the Gemini and was like, what's up? I said like, yeah, I need an idea for yeah, this is way too tiny, but it doesn't really matter. Like I need an idea for a talk, for like a meetup or a conference, and Gemini was like modern C++ idioms, what's this? Effective debugging, building robust and maintainable C++, like all the cliche stuff that everyone talks about. And I was like, yeah, that's like too similar to everything else. I need something different, something wild. And I guess some people got the reference. And so the Gemini was like, C++ and the art of self-modifying code. Don't try this at home. And then writing C++ compiler in C++, why you shouldn't. Although I think like big parts of both GCC and client are in C++, so I don't know what this means. Quest for the shortest possible hello world, and I don't know, some other stuff. But this thing like self-modifying code sounded interesting, so I was like, yeah, can you give me like more information about it? And it's like, generally it's a terrible idea. Like it starts off, okay, starts off with like self-modifying code is what it sounds, it is the code that modifies itself. And then like it's a terrible idea, like don't do it. And then like how to actually do it, which is basically find the code, modify it in memory, and then like instruction encoding. Basically, sometimes you will need to like flush the cache and stuff like that. Give me an example in C++. Who here thinks that this is going to work on the first try? Who thinks that this is going to like compile and work on the first try? Well, it's going to compile, but is it going to work? I mean, obviously not.
No, you cannot write to where the code is. This memcopy will break.
Yeah. Just like this, it's not going to work. But okay, at least right. And then like what the talk could cover, and like important notes, and like the important notes is like, this is highly advanced topic. I disagree with that because it can be, but the stuff I'm gonna show is not. Like I had less than a month to prepare this. There is no way I can like get to the level Gemini thinks I need to be. And also like don't use this in production environment. Probably the most useful thing here. And then I'm like, okay, can you like give me some resources, and it's like some books and stuff, and I don't have time for that. So I'm like, I need some like articles, blog posts, stuff like that. It just keeps giving me books, and I know. Then I also mentioned that like I'm actually using an AMD CPU because I noticed it was talking a lot about Intel. It doesn't actually matter because it's all about the x86 architecture, but what did I know? At this point, I kind of gave up, and I'm like, okay, yeah, like, you know, you did your best, whatever. Yeah, these are more resources, and like, all right, thanks, love you, bro. And the Gemini said, love you too, bro.
That sounds gay.
I want you to remember, first ignore this. If your bro doesn't say love you back, it's not a real bro. That's just an acquaintance. So, okay, I even liked this response. I give it a thumbs up. Not homophobic like some people here, so I decided to like go with this topic because of this. So, it said to talk about the history, the dangers and ethical considerations, technical details, live demo, and then like alternative approaches and security implications. So let's try to follow it. It's actually quite a terrible way to structure a talk, but you know what? He said love you, so I will do it. The history, well, there is very little of it on Wikipedia, and I haven't really found much elsewhere. Basically, the first ones to show it were the IBM in like 1948, where like, yeah, they had a code that was able to, you know, modify itself. The whole thing is that the code is in memory, and you can change memory. Because like the things like variables and data and like images and code and stuff is just like the eye of the beholder, sorry, not beholder, like the observer. In reality, it's just ones and zeros, so you can change it with like some caveats, but yes, it does work. Generally, like this used to be a common practice back in the days because you had very limited memory and the CPU and stuff, so you needed to use these tricks. Like one of the things was that you didn't actually have function calls or like subroutine calls in some assemblies, so you needed to do some like magic with this stuff. And it's generally used to protect like the licenses of the like paid software, like video games, which, you know, worked great because no one ever pirated a game or like cracked it. And like also one nice example is dynamic linking is kind of like self-modification, because when you compile a code and you don't know where the compiler doesn't know where the other function that you're supposed to call is going to be, it just leaves some placeholder, and then during the linking, it will like fill in the address of the stuff. So it's kind of a self-modification. Now, as far as the definition goes, it's, yeah, code that modifies itself while executing. And this is an important note. This is used in cases where self-modification is intended, not when you like mess something up and like buffer overflow or, I don't know, get hacked or something like that. Again, mostly for performance reasons, like instead of having if else and like couple of branches, like couple of execution paths, you have only one, and then you just modify the stuff that you need to modify, and yeah, it works, hopefully. Now, for the ways to achieve this, the simplest, well, maybe not the simplest, but the one I will be showing is the overlay existing instructions, which is just like you have the, like, when you're running the program, it's in the memory, it's in RAM, and then like you just mess with the instructions there and have different executions. Then there is like you can create the whole new sequence of instructions somewhere in memory and then execute it from there. Create a modification. Yeah, so this third thing, like one of the examples for this would be the eval function in Python or JavaScript or like stuff like that, where you can pass to the eval function a string that's supposed to be like well-formatted Python code, and then it's going to do the whole thing of parsing and like evaluating and then give you the result. And then, yeah, you can just create a whole new program and then execute it. Let me see. Luckily, I actually have some notes, but I think I went through everything. Okay, so the dangers and ethical considerations. Well, if you are actually considering using this in any like kind of production environment or anything like that, you shouldn't. It's a good thing, like it's fun, but don't. And like the things you should consider, I don't know if these are like ethical considerations, but these are things to consider, such as do you hate your colleagues? I see some nods, so I guess some people hate their colleagues. Okay, like do you hate debugging using a debugger? Because GDB will crash if it's going to assume that the instructions won't change, and then when they change, it just crashes. Do you want your colleagues to hate you or your future colleagues? Because like you will probably leave, and then someone will come and they will curse you. And like, are you like doing this just out of spite, like pure malice? And the final would be the most important one, actually. Like, are you sure you know what you're doing? How many of you here would like consider yourselves experts in assembly, or like not even experts, but like no assembly? Okay, one. But you still shouldn't do this.
We did it for the Git compiler, and we're just pumping instruction into buffers and executing them.
Yeah.
It's not self-modifying, but
It's yeah, but it is one of the things that's okay. Do you wanna like repeat?
no, it's okay. Continue.
Okay. I was asking more for if there is anyone online, but I guess not. Okay, like another thing to consider is that the first thing that comes up on Google search is from like science direct thing, and it's usually like malware and like crime and like obfuscation stuff. So it's definitely these days not used for anything good. For the technical details, like there are three like general I don't know, techniques of doing this. One would be just-in-time compilation, the other one would be eval, and then there is assembly. And the assembly by itself is just amazing. So, just-in-time compilation generally works in a way that you write code. Like one of the examples is Java. Java and C# I think both use this. You write your Java code, and then it's compiled into bytecode, which is not the Java code, but it's not the actual machine instructions. It's like somewhere in between. And then you have Java virtual machine. You have the Java virtual machine, which like interprets the bytecode and basically compiles it before the actual execution. Now the benefit of this thing is that it can actually during runtime do the optimizations, like if it sees that you're often using some code path or something like that, it can optimize it and stuff like that. The other approach is I think by Python, which is you have bytecode, but it's only interpreted. It's never actually compiled into the assembly or like machine instructions. Did I miss anything? I think not. It's fine. So the second thing is eval from Python, and basically you give it a string which is supposed to be like valid Python. It will parse it, it will compile it to bytecode, it will evaluate, and then return the result of the evaluation. And like these are some examples, pretty much basic stuff. There are limitations, like it can only evaluate expressions, not compound expressions, meaning you can't have if, else, for loops and stuff like that, but you can do some. So, I mean, like when we got const expert in C++, it was just one return, and people did wonders with that. So you can probably do stuff here, or you can just like hack someone because they're evaluating untested code. And then we get to the assembly. Now the assembly things are very, very simple. In a sense that basically you are down to the, well, as close you can get to machine without actually like fiddling with the bits by yourself. And yeah, I mean, there will be examples, but yeah, assembly code can like change itself by itself without needing anyone from the outside. And yeah, sometimes depending on the architecture and stuff, you might need to like clear the CPU cache because the CPU will like load some instructions, and then like if you are changing code that's like too close to the instructions that you are currently executing, it's going to be cached and not executed and stuff like that. Now this is like C++ memory model. And yeah, like there are, you know, the stack, the heap, and like the stuff like that, and then there is code down there, which is the actual code, you know, the instructions, and this is how we see it, and this is how the operating system sees it, and stuff like that. But in the end, it's just like ones and zeros, and if you can like mess with stuff here, you can mess with stuff here. There are some things stopping you, but you can overcome them very easily. So C++, but in reality, there's nothing really specific to C++, it's C. Yeah, you probably all know by now that C++ is basically just like syntactic sugar for assembly because it will go down to assembly. And then you are again working with assembly. So as the Gemini said, like you basically compile your code into a binary, disassemble it, look at it as if you know what you're looking at, find the place you want to modify, and then like this is like the only part where, you know, someone is actually preventing you from doing this, which is the code itself is usually in the memory in like read and execute. It has like read and execute permissions. It's like memory mapped like that, whatever is the correct term. So you will need to add the right permissions for that, and then like make the modifications, and then like if you're nice, you put it back to like read and execute, and then clear the cache if you need to. Microsoft actually, like in a way, supports part of this by this thing called hot patch, and also like G++ and Clang, I guess, assume that this is a good idea. But they, like, this is very nice. They put MS in front, just to know that this is coming from Microsoft. This was not like their idea. This is like, they will support it, but they didn't come up with this. In essence, if you compile with this hot patch, and I think you need another flag for linking, you can find it on like Microsoft site. Compiler is going to put like, I think 8 bytes in the beginning of each function, which are just not used. It's like no op operation. And the idea is that you will later, if you need to, overwrite these 8 bytes with a jump instruction to like some other function that you actually want to be executed instead of this. So this is some like hot patching, like fixing stuff during runtime without restarting anything. And I'm not entirely sure how this is supposed to work. Like, because my assumption is that you have, this is supposed to be used with DLL. So like I have a DLL that I'm using, and then I want to like, I have a fix for this function, and the fix is in some other DLL. So like I want to have a jump from here to here, and like that's hopefully supposed to work. I don't know. But I mean, this is like a general idea called like hooking, where you know, call some other function before your function, or like move to some other function. But I don't really understand how this is supposed to be used like during runtime to fix bugs. But I guess people from Microsoft actually know. And now for the live demos, just without any caution, it's like reckless abandon. So this is going to be a bit difficult now because I'm supposed to look there and not here. Isključi se. I have no idea how this is going to work. Why is it half the screen? Ada. It's so tiny. Oh, 30 plus. Okay, good. Okay. So this is some basic assembly that's just supposed to add two numbers and then like store the result into this result variable. And I don't know why the code is not highlighted because, or am I colorblind right now? But yeah, it doesn't matter. We will not spend too much time on this, hopefully. So, well, I took this off the internet, so I can't really say that I know exactly like what is what. But basically, these are the variables, and like you need this section text, which I saw like in a couple of assembly tutorials that I saw. And then add is the function which is supposed to do what I want it to do, which is like load from the num1 into this AL register, and then add like the value of num2 into the LA register, and then add the value from the LA register into the result, and then you know, you have a return. And then there is a start. The start is where the execution starts. So this is basically like a main function. And now I'm going to comment this because we will need this later. This is the actual like self-modification part. And now without the pretty colors, I don't know if this was actually properly highlighted, but whatever. It's so tiny. Okay, yeah, and the start just calls add and then calls add again, and then there is the exit, and basically you need to put like 16 to EX register, which is like telling the CPU or whoever that you are calling exit, and then I'm putting like result into the EDI, and that's going to be the return value, because printing is actually much more difficult than I assumed, so I gave up and I decided I'm just going to, whatever is the result, I'm just going to return as the return value of the execution, so we can see that something actually happened. And now I need to make this larger. Code and okay, so yeah, NASM is like the compiler, and LD is the linker, and this is going to compile the code and then going to link it, and it's going to work. And if I execute it, nothing happens, and then I look at the, where is the question mark? Oh, okay, yeah. So if I look at the return value, it's 30, and the values are, okay, and the values are 10 and 5, and like 10 and 5 is 15, and twice that is 30, so everything works, it's great. And now if I uncomment this line, and then I go back here and try to do the, oh wait, actually I forgot to actually show the line that's supposed to do the magic. So, so this is going to take the address of this add label or beginning of this function, whatever, and then it's going to add 7 bytes because that's how much this instruction takes up memory, and then it's going to put 42, and 42 is the like the opcode for sub. So now this is going to subtract number 2 from the LA which is actually the num1 instead of adding, and yeah. So the second call to add is going to do the subtraction, then it's going to add 5 to the total, so the result should be 20. Of course, how do I know this? No. Like the way you actually learn this stuff is called no. Is you just disassemble it and then like look at that because yeah. So this is like I guess the assembler itself really looks or whatever, but these are the important stuff, which are the actual like opcodes, if I'm correct. So this is the add, which is like, oh wait, where is it? Is it 02? It should not be 02, I'm not sure. But anyway, like the way I figured out that I need to move 7 spaces from, yeah, actually 02, yeah, should be fine. From the add is that I just saw that like the beginning of this instruction is like 7 bytes away from this one, and I also put a sub there, and then like when I did the object dump, I saw like that there is 42 here. It wasn't 42, it was actually something else in hex, so I needed to move it to figure out what the actual value is. And now, did I think I did. Sure. And now if I try to run this, segmentation for core dump, obviously. This is because, well, the operating system doesn't want us to do this. It will assume that this is like a virus or something like that. Let me see if I can, no. Okay, cool. So yeah, if you do like readelf, you see here, like this is the actual code that's executing, and you see that it has like read and execute instead of like read and write or whatever. So we need to change it, and there are probably better ways of doing this, but no, not edit code. So looking at this, using my astute understanding of the universe and the code and stuff, I know that there is a 5 here that I need to change it to a 7, and that's like in Linux, like 5 is read, execute, and like 7 is read, write, execute, whatever. And it's like this 5, if I'm correct. If I can just go to it. 7. Yes. No. Yes. And now, if I execute, it didn't crash. Good start. And then, if we do echo, we said that the result is indeed 20, so it actually works. I'm as surprised as you are. So that was like the first and the simplest example. Are there any questions about this? Probably should have like, well, it was probably obvious when I asked like if anyone here considers themselves an expert in assembly, because I'm not. I watched like a couple of 20-minute videos, so I know just enough to figure stuff out. Let's go into the hooking, the Microsoft thing. So in GCC, not sure about Clang. Clang actually has a compiler flag, and GCC has an attribute. So like you say ms hook prolog, and And then you have a function that you want to be hooked, and then you have a function you want to hook into. Now here I use C-style casts simply for the reason that I don't want this to be associated with C++. So no other reason. Here I basically call the function to be hooked with 1 and 3, and it does 1 plus 3, so it should return 4. And then I do the hot patch thing, and then after hooking I call it again with 1 and 3, and then it should return 3 because the hook does like, it's not module, multiplication. So I put these functions in this helpers header because I actually use them in like multiple places. Not a magic function. Okay, so first thing is like we need to make the page writable. So there is first the thing get page size. This is from like C Linux stuff, and you give it an address, and then like it gets the page size, and it's going to like do this to align it to the actual beginning of the page and not somewhere in the middle. And then there is mprotect where you give it address, the page size, and then like what you want what permissions you want to have on this page. And I mean, I just check here if it's 0 because that means it's fine. If it's not 0, then something went wrong. Like, do people in the back actually see the code? Or? Okay, I mean, you could have complained sooner, but whatever. Yeah, then I have another function that makes the page read and execute. Like, could this be like one function where I pass the writes, whatever? Yes, but I decided to do it this way, so whatever. And then there is the hot patch itself. So first, we need to make the page writable, and then we need to calculate the distance between the function that we want to hook into and, well, yeah, I don't know what's like the correct terms for this stuff. So like there is the function that I want to be called instead of the function that I'm calling. So I need to figure out the distance between those like two functions. So first, and that's just like calculated by like the address of the function you want to hook into minus the address of the function you're hooking from, and then minus 5. 5 is because the jump instruction is 5 bytes, and like it calculates from like after itself. So 1 byte is the actual like jump. No, it doesn't work. Just give me false hope. Sorry. So the E9 is the jump, and there are multiple like versions of jump. This one is like I think a relative jump that takes like a 32 byte integer, and then basically from this distance from the functions, I need to separate it into bytes because I'm writing like single bytes into memory unsigned charge instead of whole integers. So yeah, just like I cast the value and then like shift by 8 and by 16 and like 24 and get all of the bytes. Do a simple mem copy and then like make the page read and execute. How do I go back to? Okay. Not really required, but it should be nice to do that. Hooking. Yeah, there is not really much to add here. So yeah, you can probably do this with like void stars or just char stars or whatever. I think the first blog post I saw used unsigned char pointers, so I decided to roll with it. And now to actually compile this stuff. Penalty. Yeah, by the way, the only reason I added this is because, as you can see, no warnings or errors. Fascinating. So I'm going to do an object dump of the no, pressing the wrong button. Object dump of the hooking. Like, feel free to make small chat like while I'm struggling with this, the silences on the hooking assembly. Good. Let's see. Hooking assembler, and if you go to what? No, search here. Yeah. So this is like to be hooked, and this is like hook. Okay, hook, and there are some like other things that compiler adds. And here you see these like 8 bytes that are there for us to mess with. This load effective address is basically going to just load the RSV into itself. It's not going to do really anything. The reason like you have this one Leo, whatever, instead of like 5 separate no ops, because there is like, I think it's 90, the opcode for the actual no op thing, which does nothing, is that you want this to be changed like in one instruction. Like one other thing that this guy from the blog where I took this example from did was make sure that the address is 8-bit aligned, to make sure that this actually happens atomically in one operation, in case it's like multi-threaded, and then like you have one thread that's like going through. If you have 5 separate like no-op operations, you have one thread that's going through, I don't know, the third of them, while the other thread is overwriting stuff, and yeah, you get the issues. This way, like, it's safer. And you also see that here in the hook function, there is no this like no-op operation, so no hooking there. And now, if I execute hooking, yeah, you see like before there is 4 because it's like 1 plus 3, which is 4, and afterwards it's 3 because 1 times 3 is 3. If I can find the cursor, and yeah, again, like the same function is called bytes. Any questions about this? No, obviously not. And then we get to the optimization. It's about what I call optimization. So there is a magic function, and it does something, and then like I optimize the magic function, and it still does the same thing, but better. What is the magic function, and what does it do? It just like accumulates the values in the vector, but there is this static counter, and like if the counter is less than 5, the counter is added to the sum. Well, it's like 5, including 5, because this is like post increment. Otherwise, it returns just a sum. And now we're going to compile G++, but not hooking. There is an optimization. CVV twice. It's optimization. Okay, and if I do object dump of the optimization, optimization. Okay. Here. And it's optimization assembler. So if I go now to the magic function, yeah, I mean there is stuff here. It's happening. So okay, I recognize vector I. No, no, I don't know, vector something. Vector, yeah, this is vector end and vector begin, and then there is accumulate, and then again there is like a bunch of stuff here happening. Like the stuff that I can recognize is compare. So like this is the compare if the counter is greater than, well, 4 in this case. 4 in hex is still 4, right? In decimal. Yes, I guess. And then like if it's greater, jump to somewhere, and otherwise like jump somewhere else, and then like leave. The point is, you know, after the first 5 iterations, this is pretty much useless. How much of it is useless? I don't know. So what I did was I just like wrote another function that didn't have the compare and the jump and all that stuff. I looked at the assembly and I realized that basically after this here, after the call to the accumulate is already going to store the correct return value into the correct register and stuff. So basically from here, I think I just need to leave and then return. So that's what I do. And no, not yet. And so the helpers, okay, helpers. So I have the magic number. The magic number is, well, basically where in this function is the place where I need to make the change. It's 78. Fun fact. I have done this on the Windows subsystem for Linux. I've done this on this laptop, and I've done this on my PC with Manjaro. All of them, for all 3 of them, I use GCC with no optimization flags or anything like that. All 3 cases gave different assembly, and the fun thing was when I used the same. Also, I had a virtual machine, and there was also different. So there was 60, 74, 78, and I don't know what was the 4th number. And it was fun because in some cases, if I put the wrong number, I just get a stack trace. I get a core dump, things break. But one time I wasn't getting a core dump, I was just getting random numbers because I was leaving at the wrong point in the function and just getting whatever was at that point in the return register. So as mentioned, you should know what you're doing. These are the actual instructions, and they are just taken from the assembly, and it's this 48, 4B, 5D, yeah, I think it's that part here. Yeah, it's that part here. So basically this is after calling the accumulate, I just need this. I don't need the compare, I don't need the jump and all that stuff. And I have compiled already, right? Yes. Yeah, well, I needed something to get there. And if I now run this, it's going to work. So before, the cooking, where is this? Optimization. So yeah, I basically have a vector with values 1 to 5, and then I call magic function 5 times. I do the optimization because I know that after these 5 calls, the whole comparing and stuff doesn't make sense anymore. And then I call it 5 more times. After the first 5 calls, there should be 165 because 10 times, yeah, these are 10 calls. 10 times 15 plus 15 of the counter, so 165, and here is just 150. And that is indeed what we get. No stack trace, nothing crashed, at least like this time. And the obvious question now becomes like, is the optimization actually worth it? So I, of course, have a benchmark. Super, like, amazing benchmark. One case is where I just call without optimizing. The other case is where I do the optimization, and the third case is when I optimize, but I pause the timing during the optimization to see like how much like just the function is faster, because this actually, like, especially when the number of iterations is low, this takes like a lot of time. And yeah, like I do the first 5 iterations always like this, and then I do the optimization. And yeah, so there is like, oh no, this was only for the perf. Yeah, I will show that. Basically, it went from like 100 to million iterations with like 100 step and like about 100 iterations for each value, because otherwise when it gets to million, it just does 1 iteration, and that's not really statistically significant. The results, not really visible, but not much of a difference, unless you look at the relative, in which case it's sometimes worse, it's sometimes better. Who knows? The green line is the baseline without optimization, and the orange and the blue ones are like with the optimization, as you can see. Like in the beginning, it's actually much worse to do the optimization because, well, first of all, the optimization like takes some time, and probably because you're messing with the pages and stuff, the OS is going to like do some stuff. Maybe it's going to flush the instruction cache or like stuff like that. Then it's, I mean, there are differences. Sometimes it's better, sometimes it's worse, but it's unpredictable. Then I decided to like run perf stat on the benchmark, and this is the case with like with like the loops have million iterations, and there is 100 iteration for each. This is the case without the optimization. Yeah, I mean, like there is it like 27, no, 272, no. Yeah, 27,234 branch misses and like a bunch of branches and stuff. With the optimization, there is like a bit less. Yeah, there is like a bit less branch misses and like a bit less branches. And also, it's a bit faster, as you can see. It's like 3.6 seconds. This is like 3.59 seconds. Now, the thing to note here is that I cherry-picked these runs because these actually prove my point. Not consistent, like not even remotely, but I assume that like Google Benchmark itself just like added a lot of overhead to, you know, this stuff. So I wrote like a raw benchmark, which just calls the function, which basically does the same thing that the Google benchmark does, but without the Google benchmark. And then I run that for like 100 iterations. And then in this case, you see like with optimization, a lot more branch misses than without optimization, but it's like a bit, is it like a bit faster? Wait, this is like, yeah, so this is with the optimization. It's not even faster, it's slower. But then there is like another run where it is faster, and I don't know. The conclusion is that I don't know how to do like benchmarking, and also optimizing that small thing on top of calling the STL and like who knows what and where, probably not worth it. On top of the fact that you can really mess stuff up. So I guess the risk to reward ratio, not worth it. But you know, there are people from the Linux that write on Linux kernel, and you know, they know programming much better than me. So they have this static keys thing, and their idea is like somewhat similar to like what I was doing. Basically, if you want this thing, okay, so there is like static branch likely, and there is static branch unlikely, and then you have a key and stuff like that. The thing it does here is that if you have this like key enabled, and this, yeah, this is confusing with the false. I don't know why they use this example. But basically, if this branch should execute, here you're just going to have like unconditional jump into this, this here line. Otherwise, I think it's going to be a no operation. So basically, there is no like compare, there is no checking of anything and stuff like that. They do like self-modifying code. They change the code. If this should be executed, just execute it. If not, not. And like whoever did this also did a benchmark and showed that there are actually less branches, and there are, so I have it here. So there are 0.7 less branches, and there are 12% less branch misses. Like, and there are 0.2% less instructions and 2.8% less cycles, and 1.4% less runtime. No, maybe they did the same thing as me and just cherry picked the runs that show the result they wanted to show. Maybe they know what they're doing. I don't know. I can't be the judge. Yes. Any questions? Yeah, so, sorry. The magic 78 is like when you go into the assembly, this is like the place where I want to, this is the place where I want to insert my code. And like this is the beginning of the function, and then I just like subtract these two addresses, and like that's where I want to do. Oh yeah.
Also, you actually counted 78.
Yeah, I mean I just like subtracted using hex code. Yeah, yeah, yeah. I forgot to actually show the actual optimization, like the optimization, but it basically does nothing. Like it makes the page the same thing as the hooking, makes the page writable, and then like copies into the like correct place the instructions you want, and then makes the page executable, and then like in the, yeah, I knew I was gonna skip something. No. Go back here. I didn't show the code for the optimization. Yeah. Yeah, like when optimizing, just get the address of the magic function and then add the offset of the place where I want to make the changes. So like for this, you just need to disassemble and like calculate where you want to make the changes. Right back on the presentation.
Do you have other issues with operating system trying to stop you from doing it? Something like I don't know, memory randomization, or just when you fix that stack overflow issue, or when you make page writable, everything has worked.
Yeah, in my cases, yes. I have seen like the write XOR execute thing, where on some operating systems it's not possible to even make a page writable and executable at the same time. Or even like if you remove the execute and try to put write, it's going to stop you. Like in some operating systems, I think it's going to fight harder to like not let you do this. But in this case, no. But I didn't have any issues with the like the randomization stuff. Should be.
Yeah, so, yeah, just going back to this example. So if you said that there are no compares when this static branch unlikely is
I will just open the. If I can see it, probably should have increased the resolution, the actual page, because hopefully they explain it better. Static keys. There is a.
Can you maybe just make the screen a little bit more bigger?
Yeah, sure. They didn't put the else branch here. But this is like the example with the jump labels generated. Yeah, unfortunately, it doesn't have the. It doesn't have the example with the, I actually tried to like create an example for this, but I couldn't find the instruction. So what I think happens, if I remember correctly this, but you can like read it, and I don't know why they use like false and unlikely, because it's more difficult for me to keep the logic. So let's assume that this is true and this is likely. So if this key is enabled and this branch is likely, which I guess is the same thing here, then here, instead of having a jump, you have a no op, and it just like goes into this thing. And if this key is disabled, then you have an unconditional jump into the else branch, or maybe even like outside if you don't have an else branch. It's shown. So this is like if the jump labels are enabled, and let's see, print K. Yeah, so there is this XOR EAX, which is just like basically a no op. So yeah, this would be the if. This would be the, well, no. This is where you would have this, yeah, XOR, where is the jump? Oh, the jump is up here. No, there should be some compare somewhere here. Oh yeah, there is a jump here. This get bid.
Jump not in.
Where? This.
Yeah.
So yeah, is it? No, this is get bid. Move card. Pop accelerate. Move. It's a bit different. And then there is a jump. Well, okay. Yeah, there is the same jump here. There is a jump here. So it's this jump. Jump not equal. Yeah, I wish a new assembly, but.
Yeah, I think how it works usually, I mean, with likely and unlikely, is that you get to choose the order of how the branches are. Or, I mean, if you have the likely scenario, you're going to do a comparison anyway. But then, when you do a conditional jump, basically, if your test is false, then you're just.
I wish you took the microphone. So.
Yeah, so the way it usually works with likely and unlikely is that you get to choose which branch goes after the conditional jump. So you need to have that test, and you're going to do a conditional jump. But if the condition is not fulfilled, you simply you don't perform the jump. You just keep going. I think the reason for that is that you're going to have like the instruction cache populated with those instructions, and then that's probably faster.
Yeah, I think this. I mean, again, you can just go and like read through this, or maybe even find a way to play it. But I think this is like, yeah, that's the point, like of the likely and unlikely. Whether you want the if branch to be no op, or you want the else branch to be a no op. Like whichever is a no op is actually the faster thing. Because like you still need to jump into the else branch, which is still slower than this. Yeah, thank you. Anything else?
Is this just for Linux kernel code, or this is like for regular users?
No, this is for Linux kernel, and I couldn't find. I found some guy that had some like implementation where users can, but it wouldn't compile, and that was like yesterday or like the day before then, and I was sick and I couldn't.
I think this is a general used technique where this kind of performance thing matters. I think GCC also has a built-in keyboard for it. It's built-in spec or something like that.
this is, no, I think that's a different thing, but this is actually built on top of ASM Go2. This is built on the GCC's feature which allows to jump to C labels from assembly code. And I don't know how that actually plays into this because they never mentioned it here, but yeah, I watched like one talk about this thing, still didn't like fully understand it, but I didn't really commit too much to it, so some other time. Yeah.
Yeah, I sent you this, so maybe you can show it. Discord. There's a paper from some guys that did like a similar thing to this, but they call it static branching. So you have a branch, and then you know from a global state whether you want to execute the if or else branch. So you somewhere set the static variable that's going to do either one or the other, and then you just keep doing it. It's a case where you have like if in your code, but that's a pretty stable if, and people found out that it's much better to rely on this than on branch prediction. Like it works faster. So there's a paper that explains like that's the library. I think that's the library. So you can like there's an example of how it gets used. So yeah, here you can see you have like, yeah, they call it the branch changer. It's not very sophisticated, right? But you have like set direction true, and then you have set direction false, and you get to do one or the other. And somewhere like there's like they're referencing the paper there, but I also sent you the link to the paper.
Well, I can only see the. Where is my cursor? Where?
But there's also like the paper that shows the performance back.
Yeah, I also saw. I didn't go through the whole paper, but people were using for. Using for I think some benchmarking because again like doing like condition checks takes times and jumping and stuff like that, and if you can do you want me to like open something from here or
Yeah, maybe there's like the first link.
let's hope.
No, the first. Should be a PDF. No.
New PDF on the right-hand side.
It's too close to me.
USB.
It shows that someone actually reads the papers, unlike us, who just go to blogs and skip through most of it.
So yeah, there's a find the graph somewhere probably.
Yeah. Okay. I mean, do you mean like a chart or like? Do you
No,
mean
like a performance thing.
Okay.
See the lower line.
Oh wait. Hints. Oh, cool. Oh, it's a long one.
Yep, something like that.
Beautiful.
Oh no, this is just
The
an
cycles.
overhead. No, this is overhead of measuring. That's not that.
This is probably the same.
No, that is like.
CPU cycles, branch, standard deviation.
Yeah, maybe below you have comparison. Yeah.
Baseline and branch.
So do you see the right graph? No, the one below. Yeah. Yes, that's basically.
CPU cycles, comparison.
So you have one width.
Okay, so this like small thing is the like
Yeah,
the
that's
number of
the
CPU cycles.
distribution of CPU cycles that you take when you are using the technique. That's like the blue stuff is when you're using it without technique. Orange is when you're using it. No, it's the other way.
Same machine.
This will like read slower with their technique.
Yeah.
Looks nicer. Okay. Is that static keys? Should I even go into this actually? Good. More questions? No. Okay. I mean, yeah, that would be later. Okay, alternative approach is like whatever. Just don't do this. There is stuff like we have improved since these times. Security implications. I mean, it's mostly used for viruses, so, and operating systems don't want you to do this, so just like don't do it, you will mess it up. Like even with all the guidelines and like all the like security, like we still mess up and like create issues. This is just going to create more issues, so don't do this. Yeah, these are like most of the references. I mean, I did like skim through a bunch of blogs because they cover like 90% the same stuff as these ones, but these are, I think, the important ones. And I didn't care at this point. I was gonna go into this, the hot patching C, because it has a link to some paper, and I was gonna flex how I also look at papers, but I'm tired, I don't care. And like that's it.